Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at hypothesis testing and confidence intervals for means. So we already know that this quantity here follows a standard normal distribution, that is a normal distribution with mean 0 and standard deviation 1. So we're going to use that to perform a hypothesis test on a mean. So the claim here is that the average IQ of students at our school is 100. Now we know the standard deviation is 15. We take a sample of 50 students. The mean IQ in that sample is 104. We're going to perform a hypothesis test to determine whether the original claim here was valid. So we always start by listing our null and alternative hypothesis. The null hypothesis is that the claim is true, and then we're going to see if there's sufficient evidence to basically overturn this. So this quantity here is called our test statistic. We will denote it with a small z. So it will be the mean of our sample 104, subtract the hypothesis true mean. Remember, mu is the population mean, all divided by sigma. So that's the population standard deviation, divided by the square root of our sample size. So putting that in our calculator, we get approximately 1.8856. So whenever we get the test statistic, we now compare it to a table. So our tables only have 2 decimal places, so we'll round this up to 1.89. So from tables, we found that in the Z distribution, the probability of being less than this number, which is about 1.89, is approximately 0.0297. It's about 0.03. So whether or not we reject the null hypothesis depends on our choice of alpha. So if we choose the standard, alpha is 0.05, because our p-value is less than alpha, that means we reject the null hypothesis. So there is here sufficient evidence to conclude that the mean is not 100, it's actually above 100. So what actually is the mean likely to be? Well, we can sort of address that through confidence intervals. So we're going to use this formula here. So for the confidence interval, we take the mean in our sample, which was 104, plus or minus. Now this value sigma on root n is just that there. Now hopefully we know by now that if alpha is 0.05, z of alpha on 2 is 1.96. So if we put this on our calculator, we get an interval with lower bound 99.86 and upper bound 108.16. So we seem to have a bit of a contradiction here. By our hypothesis test, we're 95% sure that the mean is not 100, yet 100 appeared in our 95% confidence interval. Let's look at why that is. So the reason for this discrepancy is that our hypothesis test was one-tailed, yet confidence intervals are always two-tailed. So what do I mean by that? Well, in our hypothesis test, our alternative hypothesis was that the mean was greater than 100. So we were only looking at the area here at the top. We weren't concerned about means less than 100. So we picked alpha 0.05 and we basically figured out that 104 is in this top 5% of the area. This is called the rejection region. If the mean was in anywhere in this rejection region, we reject the null hypothesis, as we did. On the other hand, confidence intervals are always two-tailed. So if we pick alpha at 0.05, we split that area at the top and the bottom. And we found that 100 was just inside this 95% area. In fact, if we had made our alternative hypothesis in the previous slide that mu is just not 100, we would have had a two-tailed test like this. We would have had to consider if the mean is significantly larger than 100 or if it's significantly lower than 100. So this highlights that statistics is not always an exact science, and the results depend on the exact question that you're asking. In our example, it was reasonable for this to be the alternative hypothesis because we found a mean that was 104, and we're really interested if the mean was higher than what the school claimed. So just be aware of that. Let's now look at some t-tests. So in the previous example, we knew sigma, which was the population standard deviation. But almost always in statistics, you won't know the population standard deviation, particularly when you don't know the population mean. So when you don't know theta, we have to use a t-test instead of a z-test. Now this here, t, is another distribution called the student's t distribution. It looks kind of like the normal distribution. It's bell-shaped, but it has fatter tails, so more probability in the tails and less in the center. And that's to account for the uncertainty. See, here we're going to use S, the sample standard deviation, rather than the population. This here introduces uncertainty because S can change from sample to sample, but sigma, the population, won't change from sample to sample. Now this little n-1 here is referred to as degrees of freedom. When we're dealing with t, we're dealing with the mean. If you have n observations and I tell you, say, the mean is 20, the first n-1 observations can be any number you like. However, the last observation, if you know the mean, is fixed. So that's why the degrees of freedom is one fewer than the total sample size n. So as these degrees of freedom get larger and larger, the t-distribution looks more and more like a normal distribution. And that makes sense. As you have more observations in your sample, as n increases, that reduces the uncertainty. If you have like only 4 people in your sample, the standard deviation is going to vary wildly between samples. But if you have 200 in your sample, the standard deviation won't vary as much. So you can use this t-distribution as long as these assumptions are met. So let's look at an example. Let's say the distance run in 5 meters is normally distributed, mean 850, but we take a sample of students at our school, the mean's 1,000, standard deviation 150. We're going to ask the question, is this evidence that students at our school are fitter than average? So let's determine whether our mean is significantly different from the mean that was reported. So here our null hypothesis is that the mean is 850, our alternative hypothesis that it's greater than 850. When we talk about mu here, the mean, we're talking about the mean of all the students at our school. So this is again one-tailed. There is, of course, a very small possibility that the mean of students at our school is less than 850, but we're not really considering that here. We want to just know if our mean is significantly higher than this mean 850 that was reported. So we calculate this above here. This is called our test statistic. So that will be t equals x bars, the mean of our sample, minus our hypothesized mean, which was 850, all divided by s over root n. So s, the sample standard deviation, was 150, and there were 21 students in the sample, so root 21 on the bottom. So putting this on our calculator, we get approximately 4.58. We need to compare that with the critical t-value that comes from the table. Now, there are different tables for one- and two-tailed t-tests. We're looking at one-tailed here. So we go to the row where the degrees of freedom is 20. So n was 21, n minus 1 degrees of freedom here is 20. So if we look across this table, you'll see that our test statistic is larger than any of these. So we're going to reject the null hypothesis. Even if alpha is 0.01, we reject the null hypothesis because test statistic is larger than the critical t-value. So we can conclude that the mean distance run in 5 minutes of students at our school is significantly higher than 850. But that actually doesn't answer the question whether or not they're fitter than average. This is not a question we really can answer with statistics without a proper definition of fitness. This is the limitations of statistics. We can only answer the question about data that we have, so we can only talk about the distance run, not necessarily who is or isn't fitter. All right, let's look at one last example. So now we're going to look at using the t-test for a paired or dependent samples t-test. So that is, as the name suggests, when the data comes in pairs. So here I've got an example where people took a blood pressure drug. This was their blood pressure before taking the drug and this after taking the drug. This is one person before and after, one person before and after. So each data point is paired. So in order to use the t-test here, the difference scores must be normally distributed and satisfied if each set is. So it turns out that adult blood pressure generally is normally distributed, or approximately so we can use a t-test in this case. What we need to do is calculate the difference for each observation, in this case each person. So the first difference is -4, 128 minus 132. This person's blood pressure has decreased by 4 points. The next one's decreased by 17, the next one by 4 again, and the last one went up 2. So here our null hypothesis is that the mean difference is 0. That is, the drug didn't have any effect. Our alternative hypothesis, again one-tailed, is that the mean is less than 0. The drug did have an effect at reducing blood pressure. So we're going to use this formula here for the test statistic. So we need to calculate the mean of the differences. That's what that means. So adding these up and dividing by 4, we get -5.75. So we don't need to put anything else on the top because our hypothesized mean difference is 0. Now we need to calculate the standard deviation of these scores. That's what SD means. So that turns out to be 8.14 or thereabouts. And we put this over the square root of n. There were 4 observations, so n is 4. So putting that on our calculator, we get about -1.41. So if we go to our t table, this would be the one-tailed test again. We have 3 degrees of freedom because n minus 1 is 3. And we're going to test at a significance level of 0.05. If we locate that number in the table, it's about 3.182. So in this case, the absolute value of our test statistic is actually less than the critical t-value. When that happens, we fail to reject HO. So that means we found no significant decrease in blood pressure. There clearly was a decrease, but it wasn't significant. Now, I just use this for calculation purposes. In reality, we would never run such a test with only 4 participants. Any such statistical test would have very low power. It would be very hard to find an effect because the number of observations is so low. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.